Okay guys, so we're going to do a second practice question for the big table method or combined techniques with NMR. So just like before, and try not to look at my setup here, you should be able to remember the skeleton of the answer off the top of your head. It's really important you can do that and practice doing that so you remember it better in the long run. So if you could not look at this, have a go at answering this question, try and figure out what it is. Once you've done that, turn the video back on again. Welcome back. Hopefully you managed to find the answer. So slightly different setup here. This is probably what it would be more like in your exam. They've not given you every single graph, they've told you some of the information, just in words or some other form, maybe it'll be in a table. So we can still follow the same method, we're just going to miss certain bits out which we've not been given, or we've already been given. So we're told it's a hydrocarbon, so we know that there's no oxygens in it or anything like that. We've also been given the molecular formula already, so again from there we know there's no oxygens or nitrogens or anything like that. We are told the M+, but we're not actually directly told the MR, so we can still get a mark for that. So M+ is 106, therefore MR is 106. We would usually use this now to calculate the molecular formula. It's already been done though, so we just missed that bit out. Missed the IR bit out because it's told us it's a hydrocarbon. What we can then move on to is our carbon NMR. So I've got one at, what's that? 170, 160, 150, 145, and then one at 40. So looking at our data sheet, the one at 40 is going to be a C to C because, sorry if you can see that, because we don't have any of these elements here, nitrogen or halogen, so 40's got to be a C to C. The one between 120 and 160, we've got two choices now. It can either be a benzene ring carbon or a double bond carbon. So what I would do in this scenario is actually look ahead a little bit. Look at your hydrogen NMR, because although carbon double bonds and benzene rings crop up in the same place on a carbon NMR, they don't in a hydrogen. So we can look ahead to see which one it is. Double bonds between 5 and 6, benzene ring hydrogens between 6 point something and 8. So let's have a look. Where is it? Well, it's between 6 point something and 8. So these peaks here are going to be a benzene ring environment. Incidentally, this would also be a lot of carbon double bond environments to have. So we can say benzene rings. I'm going to draw 4. I'm not just going to draw one big one because there are 4 separate environments. If I can draw a hexagon. And then 40 is our C to C. Moving on to our hydrogen NMR, I'm going to label my peaks. Peak A and peak B. Always start on the left because that's generally the easiest peak, easy marks. I'm going to write down everything I know. That's that 7.0, 2.7, something like that. Splitting is a multiplet and a singlet. And my relative area, that's going to be important later, is 2 and 3. So let's start filling them in. Well, we already said that this is our benzene ring hydrogen. And if you look in your data sheet, between 2 and 3 you actually got a lot of choices. Probably the hardest spot to figure out. Just play process of elimination, last man standing. We ain't got no nitrogens, can't be that one. We ain't got no oxygens, can't be that one or that one. Only one left over is our benzene ring to CH. Which again, bearing in mind all our previous information, makes sense. You'd expect to have that, wouldn't you? So, benzene ring to CH. Now we come to our splitting. So multiplet just means lots, 4 plus. A singlet means 0 adjacent. Now this is why I kind of did this particular question. If we look at our relative areas are 2 to 3. But remember, we've got to check, does this equal our number of hydrogens in the molecular formula? Well, no. Obviously, that adds up to 5, and we've got 10 hydrogens there. So what must have happened is our ratio has been simplified. And the NMR machine just does this. It doesn't actually count the number of hydrogens. All it does is it counts the simplest ratio, whole number ratio, of the number of hydrogens. So that's why we have relative area, therefore number of hydrogens. really important to check this column. So clearly our number of hydrogens must be double the relative area, so I tend to put it in brackets. Some people do it as like an extra column, whichever one you prefer, 4 and 6. This is our number of hydrogens in the environment. So I've got my benzene ring and I've got 4 H's coming off it. So I'm going to have 4 times a H coming off a benzene ring, and they're all going to be identical. I've got a benzene ring with CH, and I've got 6 hydrogens in there, so I'm going to have 2 times that with a CH3, basically a methyl group coming off the benzene ring. Let's check for cross-linking. Well, we've got a singlet, so it ain't going to cross-link. Another little cheeky tip, so if you remember the last video, singlets never cross-link, because by definition, they have nothing next to them, right? Otherwise, it wouldn't be a singlet. Also as well, your hydrogens on benzene rings will never cross-link with anything else either. So don't be trying to cross-link them. So no cross-linking there, that's fine. Sometimes you don't get cross-linking. We're just going to have to stick it all together. So, space. Rub these graphs off, just to get a bit of space. Okay. So pop them together. Clearly we've got a benzene ring. Really nice little tip. If you've got a benzene ring environment, which crops up here, look at the number of hydrogens in that environment, which is 4. Now, straight up benzene has 6 hydrogens on it. So if I've got 4 hydrogens on it, how many side groups must this benzene ring have? Well, it must have 2, right? 2 of the hydrogens must have been swapped for side groups. And oh look, we've got 2 methyl groups. So if I didn't know this, I would still know I've got 2 side groups, just by looking at the number of hydrogens on the benzene ring. If I had 3 hydrogens in my benzene ring, then I must have 3 side groups. If I had 2 hydrogens, I must have 4 side groups. That's a really nice little tip to figure out how many side groups you have on your benzene ring. So either which way, you've got 4 hydrogens, therefore 2 side groups, and then both of those methyls. Big question now is though, where do they go? Well, the way you check where they go on the benzene ring is by looking back to the carbon NMR. So I can see I've got 4 different carbon environments on my benzene ring. So let's do a little bit of trial and error. I think the methyl group goes there and a methyl group goes there. Let's check if that fits. Well, these 2 will be identical. So different A and B to them, by the way. Let's call it X and Y. These 2 will be identical. And these 4 will all be identical. So that's only 2 carbon environments. We know we need 4 different carbon environments. So that can't be right. So let's have a little rejigglification of it. Try it again. Okay, how about this one? Okay, so I've got they're identical, and they're identical. So again, I've only got 3 benzene ring environments. Hopefully you've figured out the correct answer already. To get 4 different environments, we're going to need our methyl groups there. And then we've got 1, 2, 3, 4 different environments. So that is our answer. Now, just to go back to this graph a second, you might be thinking, well, surely the hydrogen here will be a singlet. And then these hydrogens, well, this one, environment 3, will be a doublet, and then 4 will be a triplet. So shouldn't we have 3 different peaks there? And in reality, yeah, that can happen. You can get different peaks. But with benzene rings, and it's partly to do with the fact they have that delocalized pi system, so they're sharing their electrons, they're linked in a way which most things aren't linked. What that does is it means their peaks tend to be really close to each other, their chemical shifts, and so they all overlap. In reality, you could get peaks down here overlapping, but in the exam they're never going to do that because it makes it too difficult for you, and you should never overlap your peaks if you're drawing a graph, because then it becomes ambiguous to the examiner. You know, if you did a triplet and then you tried to do a quartet over it, the examiner's not going to know what you've tried to do there. So don't ever overlap your peaks. except for when you've got these benzene ring hydrogens. They always are on top of each other. And if you look through the past papers, it's what the examiners tend to do. So they just group together all of the hydrogens on a benzene ring and just call it a big multiplet, is generally what they do. If they don't do that, they'll make it really obvious that they've done it differently. But again, look through the past papers, that seems to be their kind of mechanism. And then obviously this, all of the integration trace gets added together. So look, 4 hydrogens, which has been simplified to 2 to get the whole number, simplest whole number ratio. So that's our molecule. We can't do fragments to check it because we haven't got a mass spec graph, so that's us done.